All right, I am back from break. Not sure if you guys are back from break, but I'm back from break. So I'm going to go ahead and continue on. This was the example that we had just looked at using Ampere's law, and it was, moderately detailed. We had to go in and figure out what the magnetic field would be outside a long current carrying wire. And then we actually had to dive inside the wire itself and determine what the magnetic field would be, assuming that the current is uniformly spread across the cross-section of the wire. And we were able to come up with some numbers for that. So it's a good example to take a look at using Ampere's law. Okay, let's try another example with Ampere's law. What it said, this one's just conceptual. We're not going to be putting a bunch of numbers in. But it says, look, here is a way that we could run current out to a device and back. We could have two conductors, and we could avoid outside magnetic field. Magnetic fields that are, so when we generate these magnetic fields, they can actually have an effect on neighboring current. If two wires are going past each other, it's not just the force of the wire being drawn towards each other, but we could actually get magnetic fields that would disrupt the current traveling through a neighboring wire, kind of crosstalk between different parts of our circuit. Now, if I'm working with something where I don't want that effect, what I can do is I can use what's called a coaxial cable. And you may be familiar with these with music equipment or whatever. If I'm running wires out to a speaker, maybe I want to run it as a coaxial cable. So coax cables have current running through an inner conductor. Now this is typically a solid wire. And then we have a piece of insulating sleeve. And then outside there we have a second conductor. And they're listing this as some kind of a cylindrical braid. And that's often what's used. So I think this is like, coax cables like on a cable TV system, something like that. If you have a cable coming into your apartment or your home, if you look at those, they run off of coax cables. So the idea is to, here's what happens. The inside current is generating a magnetic field, so we're going to get these right-handed loops of magnetic field. Ampere's law tells us that I can ignore the current running through the outer portion as long as it's a long, reasonably straight cable. The current outside, the magnetic field effect, will cancel out. So as far as determining the magnetic field, I'm going to get some magnetic field inside this conductor itself, just like in the last problem. And then I'm going to get some magnetic field surrounding at these right-handed loops. But once I cover that with an equal amount of symmetrically placed current going in the opposite direction, Ampere's law now says if I draw a circle around here and ask, how much current am I enclosing? I am enclosing zero net current because I've got equal amounts of current going opposite directions. And so what that says is surrounding a coax cable, the magnetic effects cancel out. I'm not going to have magnetic effects spreading out of my coax cable. So now in the space between the two conductors, I will get those right-handed loops from the inner current, but outside the cable, I will get cancellation from the two currents running in opposite directions. Okay. All right. Let's use Ampere's law to look at the magnetic fields of a couple different geometries. Up until now, we've spent a lot of time looking at these long, straight wires with current running through them. But we actually use different devices than that when we want to set up a magnetic field. Having one wire running straight doesn't really give us much of a concentrated magnetic field. We can generate much higher magnetic fields by taking a lot of wire, kind of like in this example here. There's kind of an interesting visual effect. The wires here are actually wrapped around because of some kind of a visual effect in taking the photo, it's, unfortunately, when you blow this up, I can see it doesn't necessarily represent the wires very well. This is what's referred to as a solenoid. What it is it's a bunch of wires wrapped around some kind of a cylindrical base. So there's some kind of a plastic piece, a plastic cylindrical piece at the center of this, and then wire has just been wrapped along the length and then wrapped back maybe again. Maybe there's several layers of wire going on here. And what we want to find out is if I take a bunch of these wires, it's going to concentrate the magnetic field specifically through the central region. So what happens with the solenoid is we're going to get a concentrated magnetic field through the center of the solenoid. In the regions outside the solenoid, that magnetic field is going to drop off quite rapidly. So it's not going to spread out too far with that strong value. But again, we can get a concentrated magnetic field at the center. And so this is how they're drawing this. So what they've done is they've taken this solenoid. Let's say we get a vertical saw and we cut the solenoid in half along this length, and then what does it look like to us? And what it's going to look like is when I run current through it, what's going to happen is the current's going to be following these loops around the solenoid, and I'll have places, these are now currents. So the current is coming out here and out here and out here, and the current's going back in here, and it's a bunch of circular loops. Maybe it's, several hundred circular loops of current because we just take the same wire and wrap it around many, many times. Now, where could we come up with a path using Ampere's law? Where would be a good path to measure the magnetic field? Now, what we said is this, this circular pattern following the current. What it does is it gives us a concentrated magnetic field along the central region. So what's going to happen is I'm going to get this concentrated magnetic field through the central region of the solenoid, and then out the ends the magnetic fields are going to spread out. And those magnetic field lines spreading out tell us that the strength of the magnetic field is dropping off significantly, pretty fast. So we make kind of a crazy assumption a lot of times when we're working with solenoids in homework problems and midterm examples and such. What we typically assume is the magnetic field inside is completely uniform, but once we leave the magnetic field, we imagine the magnetic field dropping off to zero. Now that's not completely reasonable, but the formulas that we derive are going to give us a reasonably good measurement or prediction as to what the magnetic field would be in the central region. So if we go back and look at this solenoid, as we approach the ends, the magnetic field is already dropping off. But if we stick around the central region of the solenoid, the formulas that we come up with are going to work pretty well. So let's use Ampere's law. So the path that we're going to pick is this. We're going to run right along the magnetic field on the inside for some distance from C to D, and we're going to call that length L. And then when we get to D, we're going to make an abrupt perpendicular turn and come out of the solenoid. Well, if I make that abrupt perpendicular turn and come out of the solenoid, there is no magnetic field along that path. So what happens is, from C to D, I was following the magnetic field. That goes into my integration. But when I turn and run perpendicular, this path is perpendicular to the magnetic field, so I'm no longer following the magnetic field path. So this will not be a contribution to my integration. And then once I'm outside, where the magnetic field is really, really low, then I'm going to turn and go through that really low magnetic field. And I'm going to treat the magnetic field outside as being negligible. It's roughly zero. And then I'm going to make another 90-degree turn. So this is a little different from before. You know, before with that circular path, the magnetic field was everywhere along the circular path, and it was constant. In this case, the only place where I have a magnetic field in the direction of the path is between C and D. The other segments, D to A to B, B to C, those aren't going to contribute to the integral that we have set up with Ampere's law. So what's that going to do for us in terms of deriving a formula? So the formula is going to look like this. We're going to take that path that we just picked, and what we're going to say is that here are the constants, 4 pi k over c squared. I is going to be the enclosed current. Let's go back and see how much current did we enclose. Well, I enclosed a full current I here, and one here, and one here, and one here, and one here. You know, I've enclosed the full current I, and I've enclosed that some number of times. Let's call that number N. So we'll say that the current that runs through the Ampere's path is going to be equal to N times I. So this should actually say, I left that off, this should say enclosed charge, I, and the enclosed charge is actually N times the current running through the wires. And then this distance here is L along the path, and so the magnetic field I'm going to get for this solenoid, magnetic field of a solenoid, all those constants, 4 pi k over c squared, times N over L times I. And that's a formula, and I wrote down, you know, this is just a bit of an estimate. And this is, as long as I stay close to the central region, that's going to be a reliable formula. But as I get closer to the ends, that's going to become less and less so. It won't be as good an approximation as I approach the ends. But that's an idea of, that formula gives us a way of going in and determining how large the magnetic field could be inside a solenoid. And solenoids are pretty easy devices to build. I just need a lot of wire, right? Get a lot of copper wire. The solenoids we have in our labs, they look kind of like this, and they have 5 layers on them. And you can actually do some measurements to figure out what the length is. And they have like a kilometer of wire. So it's like a kilometer of wire or something that's been, or let me take that back. I'm thinking maybe it's 100 meters. Sorry, not 1,000 meters, but 100 meters. It's about 100 meters of wire that we have wrapped onto those. Okay, so you can get a fair amount of wire circled around and generate these concentrated magnetic fields. So anyway, here's an example. Field inside a solenoid. It says that the solenoid has been designed, it's 10 centimeters long, and it's used for fast electromechanical switching. So these solenoids are great because you can easily turn them on or turn them off. I can send a bunch of current through here, and all of a sudden I've got a very large magnetic field, and that can be used to mechanically switch something. Doorbells, for example, a lot of doorbells, the ones that actually ring something, have a solenoid built inside, and when you hit the doorbell button, it turns on the solenoid and then releases and turns on and releases, turns on and releases, and that solenoid pulls a little piece of iron into the bell and then releases it and then pulls it in and releases it. So, you know, these show up in mechanical devices like that. All right, let's put some numbers in and see what we've got. There's the formula. They tell us that we have 400 loops, or 400 turns. The current we're going to send through is 2 amps, and the length of the solenoid is 10 centimeters, or 0.10 meters. So we've carefully derived this formula. Now we're going to plug things in. Here is little k, here is c squared, the 9 is going to cancel that 3 squared. Putting all the numbers in, paying attention to the units, I ended up with 10.1 millitesla. So that's a pretty good magnetic field. We're only running 2 amps. I think some of those other examples we looked at were like 20, 25, 50, 60 amps. And so now we're down to just 2 amps. We do have 400 loops. And what we're ending up with is a magnetic field of 10.1 millitesla. All right, there is our solenoid example. Something that's related to a solenoid is called a toroid. A toroid is a solenoid where we've taken the ends of the solenoid and wrapped them around. So now we don't have easy access to the interior of this, but this toroid is designed so that it loops around on itself. Now the advantage of the toroid over the solenoid is that we can maintain a more reliable magnetic field throughout. The toroid, it doesn't have any ends. So it's not like there's a central region and then the magnetic field drops off. The toroid, we have this uniformly wound set of wiring, and as we move all the way through the toroid will have the same values of the magnetic field throughout. So that's a nice feature. So what we want to do, again, is count how many loops we've got on this toroid. Now, what we want to do is we want to use Ampere's law. So let's take a look and see how Ampere's law could allow us to calculate the magnetic field. Now, I went back to this slide because here are the paths that we want to integrate. So let's stop and think about what's going along the path. If I follow path 1, will there be a magnetic field on path 1? And you go, yeah, path 1 is going to cross through, there's going to be many currents that are enclosed. So let's see, here is the path right here that I'm going to follow through here. And the current comes through here, and it comes through here, and here, and here, and here. Those are all inside the path. Where the current comes back in the other direction, it's not inside the path. I don't include those currents. So Ampere's law is kind of this high-level theorem that allows us to go in and look at a circumstance like this and kind of exploit the geometry that we've set up to where going in and doing an integration of the magnetic field would just be horrendous. It would be very difficult. But Ampere's law allows us to go in and just count how many times does the current pass through our loop. It goes through n times. And then what we want to do is just find out, if I integrate this magnetic field along this path, what am I going to get? Well, the magnetic field is going to be uniform along that path. So let's take a look at path 2. Now path 2 is out in this region. Now similarly, we could have path 2 in here. If I'm in here, that's also a symmetric circle that guarantees the magnetic field is uniform at all locations. But since a path in this region encloses no current, it must be that the magnetic field is uniformly 0 everywhere inside. So there isn't any magnetic field here. What about if path 2 is out here? Well, if path 2 is out here, it has the current going through one direction, but it also has the current coming back out the other direction. So the currents going in through that area, or the currents coming out, that cancels out. There's no net current flowing through path 2. So again, it's a symmetric path. The magnetic field along path 2 will have a constant value, and that constant value will be 0. So what the toroid is allowing for is that we don't have any magnetic field outside. With the solenoid, we said the magnetic field outside, roughly we could estimate it as dropping to 0, but with the toroid, it is 0. if this has been built symmetrically, so the wiring is all placed symmetrically, then the magnetic field inside in this region or out in this region, it's 0. And where we do have a magnetic field is everywhere within those wires. Now, there's a little bit of variation of the magnetic field inside the toroid, and here's why. I could run the path close to the inner radius. That would give me a smaller circumference than if I ran the path through the outer radius. So let's see how that's going to show up in our formulas. So when I use the toroid path, I'm depending on this picture. So the magnetic field is going to have a constant value of B, and I'm just going to multiply it by the length of the path. The length of the path this time is a circumference, and it's 2 pi r. So path number 1 is going to be the one that runs through all those loops. This integration then would be B times 2 pi r. I can take that and set it equal to 4 pi k over c squared n times I, and that says the magnetic field within the toroid is going to be 2k over c squared n over r times the current. So the r does vary a little bit inside the toroid, and so the magnetic field will also vary just a little bit from the inner radius to the outer radius of the toroid. Now for path 2, any path that I take outside the toroid, that magnetic field path is going to be B times 2 pi r. That doesn't change, but I have not enclosed any charge, or any current. So since no current is being enclosed, that constant B field has a value of 0. So the magnetic field outside is constantly 0. Okay, so that's a very, that's a powerful, that's an example of how the Ampere's law can be very powerful if you have enough symmetry in the problem. Now, Ampere's law is not the direct way of calculating the magnetic field. Calculating the magnetic field directly comes back to what's referred to as the Biot-Savart law. And let's see what that looks like. So the Biot-Savart law derives from the magnetic field surrounding a charge. Now, we looked at this a couple times now. Here is a charge traveling with velocity v, and I'm looking at a point here, and the magnetic field, c times the magnetic field at that point, is going to be kq over r squared, v over c, times the sine of theta, with the direction being these right-handed loops for positive charges and left-handed loops for negative charges. What that gives us is a magnetic field formula that depends on how far I am away from the charge and what angle I'm looking at. It also depends on how much charge I have and how fast the charge is moving. So that's going to give me a magnitude, and then the diagram is showing the direction. Now, how would I carry out an integration process? So what we're doing now, using direct integration, is to say that we want to set up some kind of an integral. Oh, here they are. Okay. So what we want to do is be able to set up some kind of an integral, and this is what it looks like. So what we're going to do is, actually it looks like this. So this is the one from here with the charge. What we're first of all going to say is a little bit of charge generates a little bit of magnetic field. Now that's what we said with the electric field integrations too. A little bit of charge creates a little bit of electric field. This time a little bit of charge moving creates a magnetic field. Now, once I've shrunk that down to the level of some infinitesimals, what I can do is I can set that inside an integration and say that the way I'm going to calculate the magnetic field is I'm going to integrate over all of the charge distribution. I'm going to look at every little charge. I'm going to look at how fast it's moving. I'm going to look at what angle it's making its contribution from, divide through by the distance, and then calculate a magnetic field at some point. So that's how we would calculate a magnetic field based on integrating over charges. Now I should point this out along the way too. You guys are not required to do any of these integrations of magnetic fields. So Ampere's law, you should have kind of a basic idea of how we worked with Ampere's law. But these direct integrations tend to be kind of more difficult in general. And so I'm going to say, no, don't worry about doing any of these direct integrations. Now, there's an alternate way. We don't have to work in terms of individual charges. That would be the more fundamental way to approach this. But what we can do is we can take a bunch of charges, a bunch of DQs, and we can say that a DQ, see if the formula, here we go, a little bit of charge moving at some speed v, that can be written as dq dx divided by dt. Now what we can do is we can take the dq over the dt and say that's current. So what we've done with this little formula down here, dq times v is the same thing as a current integrated over short segments. These are short current segments. These are little bits of charge moving at some velocity. What that is telling me is I can take out the dq times v and replace it with I times ds, where ds is a short segment of current. So if I had a current running here, there is a short segment. That's the same effect as the charge here moving with velocity v, if that's a dq. So we can do the integration either over the charge or over the current. Either approach will work. Now all the examples that the book uses, they're going to be working in terms of current. So again, this is the direct integration method that you don't have to worry about. I'm just going to take a little bit of time here and talk a bit about what the setups look like. Here is current over a short distance. This is keeping track of the distance, so that's a distance, little r. That goes into my formula. Here is the angle, so that theta goes into my formula. And then what I'm getting is a little bit of magnetic field. Now the magnetic field I have here, it says is going to be into the board. Why is that? Well, it's because the magnetic field is going to be in the direction of dV. The current is going in this direction, so this is the direction of the velocity, but this is the direction of r. So the charge is here. R takes us out to some point, and the unit vector is pointing away from the source, from the little bit of current. And then the velocity of that current is here, so I do a right-hand rule with velocity and radial direction, and that cross product says that the magnetic field will be inwards. So that's how the formula would be carried out. What it says is I would be working from the current equation, not the charge. So I could say k times the current over c squared. I would take one step at a time, divide through by the distance, and multiply by the sine of the angle. And as you can see, that's going to be complicated, because when I move from one segment to the next, I have to integrate along the entire length of the current. When I move from one to the next, r keeps changing and theta keeps changing, and it's not a trivial formula. I really have to pay attention to each step. So again, you guys, this is not within the realm of our course. We're just trying to show you how I can start with the charges in motion and determine what the magnetic field would be at different locations. Here's another example. So this example that they used, this was for the long straight wire. Now, what do you think we get as a formula if we carry out this integration, assuming that the wire is very, very long, and we're going to end up with the very same formula that we used from Ampere's law. So this approach, the direct integration approach, works, it will give us the same formula that Ampere's law does. The advantage of this direct integration approach is that it doesn't have to be an infinitely long wire. Direct integration allows us to go in and change the limits of integration. So if this wire goes on for 40 centimeters and then it bends and goes somewhere else for 40 centimeters, this formula allows us to take that into account. It's a lot of detailed calculation, but it allows us to go in for whatever geometry we're handed and kind of systematically go through and calculate the magnetic field. But again, the problems could be really difficult. They could be difficult enough that you wouldn't want to do it by hand. You would want to write some software or something that would allow you to put in where the current is and what point you want to measure the magnetic field and let the computer follow the formulas to do that. Okay, another example that the book goes through, and again, you guys don't have to do this, is a loop. Now this is kind of interesting. If we just take one loop of current. So this time I have current going around in a loop. Now sometimes students go, well, if I have a current in a loop, isn't that enough symmetry to use Ampere's law? And it's not. Ampere's law requires that we find a path along which the magnetic field is uniform, and a current loop doesn't provide that. Now what we can do is we can do an exact calculation. This individual current loop, if you remember from last chapter, actually gives us a dipole shape for the magnetic field. So individual current loops will give us this dipole magnetic field, kind of like the field surrounding the planet Earth. Earth has a magnetic field that is shaped like a dipole. Electrons and protons and neutrons have little tiny magnetic fields that are shaped like dipoles. Anyway, this goes through all the integration. Again, we have to keep track of all the distances, all the angles. When we carry out the complete integration, what we end up with is this formula here, which is still a difficult formula. And what it's telling us is the magnetic field along the axis of a loop of current. So this is the picture that we have up here. Now, that's complicated, but we can simplify this by saying, well, what if we simplify it? What if we just look at the center point? What would the magnetic field be there? For that case, we can set x equal to 0, and our formula that we've derived here simplifies into this. So it says that one loop of current will produce a magnetic field at its center that is 2 pi k over c squared I divided by r. Okay, and that's, it looks similar to the formulas we've done before, but this is 2 pi. It's not the same formula as a straight line of current. This is one loop, and it's a different formula. Okay, so this is a bit of a review, but after everything we've gone through, and we've gone through a lot, so we've looked at some really interesting examples, but some of this has been, fairly challenging to take a look through. Let's talk about what sort of magnetic fields we actually tend to encounter. If we start with individual charges, first of all, I want to look at an individual charge in terms of its velocity. If I have an individual charge in terms of its velocity, what we've said a few times now is that c times the magnetic field for that, based on the velocity of the charge, is given by kq over r squared times v over c times the sine of the angle. So we've seen this a few times. What I wanted to introduce too is, we haven't seen it so much in this chapter, but starting in chapters 29 and then again in 30 and 31, what we're going to be looking at are charges that are accelerating. So up until now we've mostly been talking about charges that are moving at well, not necessarily a constant velocity, but we've looked at the fields generated based on how fast they're traveling. Well, it turns out that if there is an acceleration taking place with charges, we get an additional magnetic field. And mathematically, this is separable, fairly easy to separate into two contributions. One that's dependent on, at any instant, how fast is the charge traveling. And the second part, that depends at any instant, what's the acceleration of the charge. So there are what are called velocity fields, and the velocity field for the magnetic field is kq over r squared v over c sine theta. The acceleration fields are given by kq divided by r, not r squared, but divided by r. And then it also depends on the acceleration divided by c squared, not c, but c squared, times sine of theta. Now, what's important about these acceleration fields is that they don't drop off very fast. The velocity fields drop off like r squared, so if I move away from these charges, the magnetic fields drop off pretty rapidly. But the acceleration fields, that doesn't happen. Not as fast. And we can actually show that not only do we have these velocity and acceleration effects for magnetic fields, but we also have them for electric fields. So electric fields show this same property. The electric fields we've looked at so far are these velocity electric fields. But again, starting in chapter, I want to say 29, maybe 30, we're going to start looking at acceleration fields. And the acceleration fields look very different for the electric field. And so when we have charges accelerating, when they're constantly speeding up or if they're oscillating back and forth, we can generate these electric and magnetic fields that propagate over long distances. And that's what radio station broadcasts are, or a cell phone communication is done through acceleration fields, not through the velocity fields. So that's something, again, that we'll be looking at in the upcoming chapters, 29, 30, and 31. We'll be talking more and more about acceleration fields versus velocity fields. Now, for the magnetic field, the velocity and the acceleration fields look kind of similar. We're going to end up with these right-handed loops for the positive charges, left-handed loops for the negative charges that are generated, and those loops for the velocity field, the loops are symmetrically surrounding the velocity direction, and for the acceleration fields, those loops are symmetric around the direction of the acceleration. Now, if I've got charges oscillating back and forth, like this, then I'm going to have the velocity and the acceleration fields along the same axis. But I won't necessarily have them in the same direction, because if I have charges oscillating, there are going to be times where the acceleration and velocity are in the same direction, where these two effects would add together, but there's going to be times when the acceleration opposes the velocity. And so I'm going to get the difference between these two. In either case, it's the acceleration field that over long distances transmits away from these oscillating charges. And so for a radio station, you know, they have an antenna, and they're broadcasting through their antenna, and they're oscillating current in that antenna to generate a signal that will travel long distances. So long range microwave communication or radio communication is done through the acceleration fields. Now, also with magnetic fields and with electric fields, we have the possibility of generating fields that have this, what we call dipole geometry. Now, as far as the magnetic field, where we've seen those show up, is at the level of a fundamental particle, an electron, a proton, we're going to end up, or neutron, we're going to end up with magnetic fields associated with each one of those particles. Because those particles have an intrinsic spin, angular momentum, and because they have, in the case of the electron, it's just flat out charged. In the case of the proton and neutrons are made out of other particles called quarks, and the quarks have charge. And the quarks also have intrinsic spin. So the spin of the proton and the spin of the neutron are a result of the spins of the quarks that they're made out of, and the magnetic fields of the proton and the neutron are a combination of the magnetic fields due to the quarks' magnetic fields that the protons and neutrons are made out of. So when I'm looking at these fundamental particles, I have to remember they all have magnetic fields. Electrons, protons, and neutrons, they're going to have these dipole-shaped magnetic fields. And then the big scale stuff, right? The astrophysics stuff of planets. You know, and planets may or may not have a magnetic field. Not all planets do. But certainly when you're looking at stars, or if you're looking at large accumulations of material, you're going to find magnetic fields being generated by large stars, for example. Those magnetic fields are going to be very much present astrophysically. All right, so those are kind of this is kind of the takeaway, is that we're going to get these magnetic fields. They have these different geometries to them. We've taken a look at a good number of examples. Take a look at the homework problems. Go back from chapter 27 and 28 as needed, and then stop by office hours so we can get these things sorted through. Now there is a last topic that we can talk about quickly here, I guess. And this is with reference to ferromagnetic materials. And this is what we talked about the beginning of this chapter, or was it 27? So when we looked at magnets, way back, I think in chapter 27, when we looked at magnets, we said that the magnetic fields of magnets are due to the spins of the electrons. It's the magnetic fields of the spinning electrons that contribute to make those materials magnetic. Now, in almost all materials, we can't get the spins on the electrons to stay aligned. The electrons will end up just randomly oriented. Their spins will end up being randomly oriented. But with iron and nickel and a few other materials, these materials, we can get alignment between the different regions. Now, regions like, materials like iron and nickel, they already have these small regions where the electrons have aligned. When we magnetize something, what we're doing is we're taking something that is randomly aligned, and we're converting it into something where we have greater alignment. So what we're looking for is partial, not sure if we ever get full alignment of all of the spins. So placing them in external magnetic fields, we can magnetize these materials. Okay. And then here's kind of a summary of some of the formulas that we've looked at and some of the different techniques we've used to calculate magnetic fields. I think I'm going to go back to this picture as just kind of a basic set of pictures of what is it that is creating the magnetic fields that we're looking at. Okay, again, whatever questions you guys have, stop by. We will get those questions looked at.